Very good evening, good morning, and good afternoon to all the IEEE Region 10 members all around the Asia Pacific region. So here we are today at the third IEEE Region 10 talk of year 2023. So I'm Varnika Hippola, the student representative of IEEE Region 10 Student Activities Committee, and I'll be your moderator for the day. So today's topic is a quite interesting one. It's innovation technologies for highly safe and energy efficient gallium nitride devices. So in order to introduce the speaker and to welcome you all, I would like to invite Professor Jennifer Chua de la Cruz, Professor at Mapua University, Philippines. She is the Student Activities Committee Chair of IEEE Region 10. Prof. Jen, over to you.
Hello, everyone. Yes, thank you, Warnika, for the warm introduction. And good afternoon, good evening to all our guests and participants in and outside Region 10. And of course, the vibrant organizers of R10 Talk webinar series. Well, allow me to welcome you to another much-awaited R10 Talk for 2023. Well, this is actually the third, as mentioned by Warnika, and the title is Innovation Technologies for Highly Safe and Energy Efficient Gallium Nitride Devices. Well, personally, even though I'm one of the volunteers behind 10 Talk, I still feel excited to connect and invite our speaker for today's session. With the wide applications of GaN devices from biomedical, power electronics, robotics, space, and so much more, where are we right now in terms of safety, speed, tolerance, and efficiency? In this session, we get to hear updates on gallium nitride from the expert himself and recipient of prestigious awards from the Japanese Society of Applied Physics. He is also active in publishing and reviewing papers and even received an Outstanding Reviewer Award for 2022. He is also included in the IEEE Electron Device Letters and Transaction in Electron Devices Golden List of Reviewers for 2022. He has co-authored about 100 refereed papers and conference proceedings. Well, not to mention that he's also an active IEEE senior member serving as a committee member of the IEEE International Meeting for Future of Electron Devices CANSI, and presently serving as the chairman of the academic committee. Currently, he is an associate professor at the University of Fukui, Japan. He actually continued his passion in teaching because I met him as a student and faculty of Mapua University in the Philippines. And so, without further ado, let us all welcome Dr. Joel Asubar.
I'm sorry. Thank you, Mom Jenny. So I would like to share my PowerPoint. Can you see now my slides?
Yes, it's visible.
Okay. Can you see my slides now, Mom Jenny?
Can. Let's go. Yeah, we can. Yeah.
Okay. Shall I start now? Shall I start?
Go ahead.
Okay. Thank you. Thank you, Mom Jenny, again, and the organizers of this IEEE R10 Talk for giving me the opportunity to share our laboratory's humble work on gallium nitride-based devices. Good afternoon. I am Joel T. Asubar from University of Fukui. I'm sorry. Okay. This is the outline of my talk. First, I will try to answer the question, why gallium nitride? What makes it special, and why is it considered the next generation semiconductor material that can complement, if not replace, silicon? Then I will discuss argon hemps, or gallium nitride high electron mobility transistors, which are one of the most studied gallium nitride-based electron devices. Next, I will discuss the normal-on issue or problem, hampering their widespread deployment. Normally on means these devices conduct electricity even without applied gate control voltage, which is undesirable in many applications. Then I will briefly introduce different normally off operation approaches to make these devices conduct electricity only when appropriate positive gate voltage is applied, which is preferable for fail-safe applications. And finally, I will introduce our own approach to obtain the desired normally off operation. We call our device recess gate with regrown barrier GaN mishaps. Well, in 2014, three Japanese scientists, Nakamura sensei, Akasaki sensei, and Amano sensei, were awarded the Nobel Prize in Physics for the invention of blue light emitting diode that enables a high brightness, power saving white light source. And what is so important about this blue LED invention? Well, it is estimated that lighting accounts for about 25% of our electrical energy consumption. Now, the most common type of light bulb used in the world today is the incandescent bulb, which produces light by passing current through a wire filament, heating it to a temperature that results in generation of light. This process is rather inefficient that only 10% of electrical energy is converted to light, the rest converted to heat. Moreover, the typical lifetime of an incandescent bulb is just 1 kWh. In comparison, white LEDs are very efficient, converting 90% of electrical energy into light. And also, its lifetime is almost 50 times that of the incandescent lamp. And because of white LED's high efficiency, it is currently estimated that in 2030, 261 terawatt hours, that's 261 followed by 12 zeros, watt hour of electrical energy will be saved due to widespread use of white LEDs for lighting. And this savings in electricity will eliminate the need for at least 31 gigawatt power plants and avoiding the generation of 185 million tons of carbon dioxide. Well, in order to realize white LED, in principle, red, blue, and green light, or red, green, blue LEDs are needed because their combination will produce white light. Red LEDs have been demonstrated as early as 1962, while green LEDs had been demonstrated in 1968. However, it took some years to realize blue LEDs. Compared to green and red light, blue corresponds to a shorter wavelength. Shorter wavelength light, and since energy and wavelength from this equation, from this relationship, are inversely proportional to each other, a higher energy, that is a semiconductor with wide bandgap energy, is required for blue emission. That means moving away from this traditional compound semiconductor, arsenides and phosphides and antimonides, and consider this nitrides, whose combination can generate blue light. Actually, during the 1970s, two semiconductor material candidates were considered for blue LEDs, the gallium nitride and the zinc selenide. Well, considering the relative ease of growth of zinc selenide, because it can be grown readily on the readily available gallium arsenide substrates, zinc selenide was highly more popular than the gallium nitride during those earlier days of the research. The only viable substrate for gallium nitride during that time was sapphire substrate, sapphire, which has very high lattice mismatch of about 16% with gallium nitride. Lattice mismatch is a measure of how much difference there is between the lattice parameter of epitaxial layers and the substrate. To enable epitaxial growth, lattice mismatch should be as low as possible. And the lattice mismatch for high quality epitaxial growth should be less than, actually 1%, less than 1%. Again, the lattice mismatch between gallium nitride and sapphire is about 16%. In contrast, the lattice mismatch between zinc selenide and gallium arsenide is just 0.26%. Therefore, zinc selenide attracted more researchers during that time. And as Nakamura sensei related at a Oyobutsuri Gakkai, or Japan Society of Applied Physics conference in 1982, there were approximately 500 individuals attending the zinc selenide sessions, whereas for gallium nitride session, there were only around 5. According to Amano sensei, he was surprised. Amano sensei was surprised to see that there were only 4 people in the room for his presentation, for Amano sensei's presentation. The chairman, Professor Akasaki, one other guy, and Amano sensei himself. And that other guy was actually Nakamura sensei. Well, in principle, it is difficult, if not impossible, to grow gallium nitride on high lattice mismatch sapphire substrate. However, in 1985, after performing countless experiments, Akasaki sensei and Amano sensei succeeded in growing high-quality gallium nitride epitaxial layers on sapphire substrates using a low-temperature aluminum nitride buffer layer. But there was another problem. In order to fabricate practical LEDs, P-type and N-type, PN junctions, P-type and N-type gallium nitride materials are needed. While N-type gallium nitride is relatively easier to obtain, the problem was to obtain the P-type conductivity, or P-type gallium nitride. In order to obtain P-type conductivity, gallium nitride is doped with magnesium. Since magnesium is a group 2 element, it has 2 valence electrons, 1 less compared to 3 valence electrons of group 3 gallium. So if a magnesium atom occupies a gallium site in a gallium nitride crystal, deficiency of electron or hole will be generated. But even gallium nitride is doped with magnesium, holes were not actually generated. And this was due to the fact that magnesium was passivated with hydrogen atoms, preventing magnesium atoms to act as acceptors. I should mention that for the growth of gallium nitride, ammonia gas is used as source of nitrogen. Ammonia, it is NH3. And this associated hydrogen atoms from ammonia forms the magnesium hydrogen complex. Eventually, in 1989, Professors Akasaki and Amano succeeded in realizing a P-type GaN after irradiating low-energy electron beam on magnesium-doped gallium nitride. And in 1992, Nakamura sensei realized a P-type gallium nitride using a simpler process, thermal annealing process of magnesium-doped gallium nitride. Not only that, he also demonstrated the first P-GaN, InGaN or indium gallium nitride, NGaN LED. For this LED, InGaN is inserted between the P and N-type GaN layers and serves as the active layer where the electrons coming from the N-type and holes coming from the P-type recombine. Note that the band gap of InGaN can be tuned, say, for 2.8 electron volts here, depending on the relative composition of indium and gallium. When forward biased, electrons from the N-GaN and holes from the P-GaN are injected into the in-GaN active layer where they recombine. And the energy lost by electrons during the recombination process is converted to photons, whose energy is approximately equal to the band gap of in-GaN, corresponding to blue light. On the final note, I just want to mention the contribution of Matsuoka Sensei of Tohoku University, who demonstrated the first successful growth of in-GaN under extremely high supply of ammonia. Because of the contribution of these scientists, we can now enjoy the merits of gallium nitride blue LED. Well, another approach, and actually the most successful approach to produce white light, is to combine blue LED with a phosphor. A phosphor is a material that it can emit light after its excitation by external energy. For a phosphor, the general rule is that the emitted light should have lower energy than the light used for its excitation. Because blue light has high corresponding energy, different lower energy colors ranging from green to red can be generated using phosphor. In this illustration, the blue light from the LED is partially absorbed by the phosphor as excitation and converted to green and red light, while other part is transmitted through the phosphor. And as a result, the green and red light from the phosphor and the blue light from the LED itself combine together to form white light. This is a spectrum of blue LED and phosphor combination. This peak is the blue electroluminescence from the blue LED, while this peak is the yellow fluorescence from the cesium-doped yttrium aluminum garnet phosphor, which is actually a broadband emission of green to red and appears yellow to the human eye. Here we can recognize and appreciate the importance of blue LED, because out of just blue light and a phosphor, we can actually generate white light. And therefore, the 2014 Nobel Prize in Physics is very much well-deserved. Meanwhile, the progress in gallium nitride crystal growth has also enabled the development in power electronics. Gallium nitride is actually a suitable material for fabricating power devices. And why is it? Now, I tell you why. This slide shows a simplified process flow of energy conversion from primary energy sources to energy that can be used by the consumers. From primary sources, energy is converted to different forms before it is delivered to final consumers. For instance, voltage generated in power plants are typically in kilovolts, but our cell phones just need 5 volts and our laptop charges at 15 volts. Generally speaking, there is a need to step up, step down voltage, or change its frequency. However, in the process of power conversion, a huge amount of energy is wasted. This loss is due to the low conversion efficiency of power devices. Much of this loss is due to the intrinsic limitation of silicon, which is the semiconductor material from which the semiconductor devices are made up of. Energy loss is power times time, and power is equal to I squared. I is the current times R. This is I squared R power times time. This is the energy loss. And here, R is the resistance of the semiconductor devices. We can see here that the higher the resistance R, the higher the energy loss. Meaning, to minimize energy loss, the resistance of the devices should be minimized. Generally, for T5 compound semiconductors, as the constituents group 5 element, antimony, arsenic, phosphorus, nitrogen, as the constituent group 5 element moves up the column, the corresponding bond length decreases. This bond length decreases. As can be seen here, the horizontal axis represents here the bond length. As can be seen here, antimonides have the longest bond lengths, followed by arsenides, and then phosphides, and then nitrides. Smaller bond length between the group 5 and group 3 element means that the bonding energy between the constituent atoms is stronger. And stronger bonding energy means wider band gap energy, which means that among the 3,5 semiconductor materials shown here, the nitrides have the widest band gap. And what is the consequence of having a wide band gap? Why it is very important to have a wide band gap? Well, the higher the band gap, the higher the critical field. And critical field is the minimum electric field that leads to material breakdown. It was shown by Hodgkins that the critical field varies parabolically, or varies as the square of the band gap energy, which means that the higher the band gap, the more robust or stronger the material is against the applied voltage. Now let's go back to the original question of how to minimize the energy loss in power devices. Again, I said earlier that the resistance should be minimized, and we can do this by employing wide bandgap semiconductor materials. And how is that? Well, resistance is given by this equation, which means that we can decrease the resistance R by shortening the length of the devices, or enlarging the cross-sectional area A. Well, enlarging the cross-sectional A is not the best solution because it means taking up large semiconductor real estate, or it would lead to big devices. For a better approach, the better approach is to shorten the length of the devices. However, shortening the length of the devices will make the devices prone to breakdown. For a constant applied voltage across the device, a shorter length leads to a stronger electric field. And when this electric field exceeds the critical electric field that depends on the material, then breakdown happens. This is where the so-called wide bandgap semiconductors like gallium nitride come into picture. As we can see, this gallium nitride has almost 10 times larger critical field, EC, than silicon, which means that for the same breakdown voltage, a device made from gallium nitride can be made much shorter compared to a device made from silicon. And this leads to a lower resistance and therefore lower energy loss. So basically, this is the line of thinking of using wide bandgap semiconductor to obtain devices for highly energy efficient devices. Now, let me introduce the argon GaN hemp, which is one of the widely studied GaN-based electron devices. Strong polarization fields in the argon GaN heterostructure result in a sheet of very mobile electrons which tend to gather along the argon GaN interface. This is called the two-dimensional electron gas, or simply 2-DEG, which has a high density and mobility that can facilitate low resistance and high power operation. Let me then talk about polarization, which plays an important role in nitride semiconductors, where polarization is the separation of positive and negative charges in the system. And the polarization in gallium nitride is due to two main reasons. Due to the gallium and nitride ionic nature of bonding, and the second, the deviation of the gallium nitride crystal structure from the ideal structure. First, let's talk about the gallium nitride bond ionic nature, causing polarization. The gallium nitride bond is strongly ionic in the sense that the electron probability density is greater in the vicinity of a nitrogen atom, which means that electrons spend much longer time near the nitrogen atom than near the gallium atom. And this makes the nitrogen atom somewhat more negative and the gallium atom somewhat more positive. The second reason the polarization is the deviation from the ideal structure of the gallium nitride wurtzite crystal structure. If this is the gallium nitride wurtzite crystal structure, we can construct a tetrahedron considering these 1, 2, 3, 4 gallium atoms as corners and these nitrogen atoms as the middle atom, like this. For a regular tetrahedron, all the 4 triangular faces have the same area. This is for ideal regular tetrahedron. However, for the actual gallium nitride structure, this is not the case. This is the actual gallium nitride tetrahedron. The actual gallium nitride tetrahedron is actually somewhat laterally stretched or vertically squeezed. And this makes the topmost triangular face larger than the other 3 faces. If the gallium nitride tetrahedron is ideal or regular tetrahedron, the centroid of the positive charges, due to somewhat positive gallium atoms, will coincide with the centroid of the negative charge due to somewhat negative nitrogen atom. In this case, there is no separation of negative and positive charges, and therefore no polarization. However, in the actual gallium nitride crystal, the tetrahedron is vertically squeezed, as I mentioned a while ago, causing the centroid of the negative and the positive charges to move away from each other. And this separation of centroids of negative and positive charges results to polarization. And this is known as the spontaneous polarization in gallium nitride. So this polarization appears spontaneously by default in gallium nitride crystal structure. For aluminum gallium nitride heterostructure, or algan grown on gallium nitride, there is another type of polarization called the piezoelectric polarization, which is the polarization due to the distortion of the crystal lattice of algan due to the difference of lattice constant of algan and GaN. Because algan has a smaller lattice constant than that of GaN, the algan layer will be under tensile strain when grown on top of the gallium nitride, causing additional stretching in the lateral direction, causing further separation of centroids of negative and positive charges in algan. And therefore, in algan layer, in addition to spontaneous polarization, there is piezoelectric polarization as well. Again, for the algan layer, not only spontaneous, but also piezoelectric polarization is present. For this orientation of algan GaN, within the algan layer thickness, we have alternating positive, negative, positive, negative, positive, negative charges. And focusing on the edges, there are negative fixed charges on the algan top surface and positive fixed charges on the algan bottom surface. The same is true for gallium nitride. There is negative fixed charges on the GaN top surface and positive fixed charges on the GaN bottom surface due to spontaneous polarization. Now, I'll explain more how the two-dimensional electron gas is formed along the algan-GaN interface. Let's consider this portion of the device: metal, algan, GaN, and substrate. And let's draw it here: the metal, algan, GaN, and the substrate. Due to polarization field, as discussed a while ago, fixed negative charges generated on the algan surface or on the left here of the algan edge in this diagram. This is a negative polarization charge. This is fixed charge. This is immobile. This is not moving, cannot move. Also, there are net positive charge here along the argon-GaN interface, and this is actually the net sum of the positive charge from the argon right surface and the negative charge due to the GaN left surface here. And of course, when we take the net sum of this turns out to be positive because the positive is greater than the negative. And finally, we have here also the negative fixed charge on the gallium nitride right surface due again to the spontaneous polarization. Now let's turn our attention to bond diagram of this device. The band gap of gallium nitride is 3.4 electron volts. While depending on the aluminum composition, the band gap of argon can be varied from 3.4 electron volts to 6.13 electron volts. Gallium nitride band gap and aluminum nitride band gap. And the combination, argon, can be tuned between these two values. For conventional argon hemps, the aluminum composition is usually 25%. By simple interpolation, we can compute the band gap of 25% aluminum argon, which is actually approximately 3.9 electron volts here. Now, the band gap of argon and GaN are intrinsic properties, and therefore their values are fixed, as well as the difference between the conduction band edges and valence band edges called band offsets. Usually for heterojunctions, this delta AC, the difference between the conduction band edge, is about 70% of the band gap difference between the GaN and argon. So that is 70% of this 3.9 minus 3.4 electron volts, resulting to 0.35 electron volts. While the remaining 30% is the delta EV, or the valence band edge offset between the argon, GaN, and this is computed to be approximately 0.15 electron volts. And therefore, we end up with these fixed values of band gap and offsets, delta EC and delta EV. Now, let's simplify our band diagram, concentrating on the conduction band edge and valence band edge EV. And put these argon and GaN layers into contact. Now, because the polarization field within the argon layer, the argon should bend in this manner. We can visualize the bending of the argon by considering that the fixed charges on both sides of the argon layer, negative on the left and positive on the right, which means that the electrons are being pushed or being repelled by this negative and being attracted to this positive. So effectively, the electrons are being pushed towards the right. And this is equivalent to bending the argon band energy in this manner to produce a slope that will move the electrons from left to right. Since delta EC, or the band offset, is constant and should be preserved, if argon EC, conduction band edge, move downward by this amount along this interface, then the gallium nitride EC should also move by this amount to preserve the conduction band offset. And voila, what do we have here? First, it should be emphasized that the band gap as well as the delta EC and delta EV are all preserved. What is interesting here is that a triangular quantum well here is created here where electrons can accumulate like this. And this is how the two-dimensional electron gas is formed. And again, the important thing to remember here is that the density of this 2-deg can be modulated by the applied voltage on the gate. However, due to this natural presence of 2-deg in argon GaN hemps, These devices are normally on devices. If an external voltage VDS between the drain and the source is applied, current flows even without applied gate to source voltage. Even when gate is shorted to source, or when VGS is 0, or gate is shorted to the source, ID, the drain current, flows. This condition is represented by this point. VGS is 0, but non-zero ID flows through the device. In order to reduce the drain current to 0, we need to apply negative voltage on the gate, or need to apply a negative VGS, which can deplete the 2D channel underneath, and therefore interrupting the current path, forcing ID, drain current, to be 0 at this applied negative voltage VGS. We can connect these 2 points and add this portion of the 0 current for more negative VGS to generate this transfer curve of typical algal hemps. This is the so-called normally on problematic issue in algal hemp power devices. Algal hemps are normally on devices with negative threshold voltage, meaning a negative voltage is required to turn the transistor off. Suppose that this is our normally on device in the actual circuit. If for some reasons the gate drive circuit encounters some problem causing disconnection from the gate, because there is no voltage applied on the gate to deplete the two-dimensional electron gas, the channel will again be formed. And ID will flow uncontrollably. For this reason, normally on devices are problematic. And normally off devices with positive VTH are more desirable. For normally off devices, if the gate drive circuit encounters some problem causing disconnection from the gate, current remains 0, making normally off devices desirable from fail-safe point of view. Now the question is, how positive should the threshold voltage be? Because the devices are geared to be operated in high frequencies where noise in the form of unwanted oscillations and ringing are expected, a threshold voltage of at least positive 3 volts is desirable to prevent false turn on and ensure system protection. So the big question now is, how do we obtain normally off operation with positive threshold voltage? There are different approaches, and these include P-GaN gate. For a P-GaN gate, a P-type gallium nitride is inserted between the gate and all GaN, causing the depletion of 2D. Well, it has its pros and cons. Its pros advantages are it is relatively stable and reliable, but the threshold voltage is very limited, up to positive 1.2 volts. And of course, it includes a very unreliable P-type GaN layer. Another approach is the cascode structure. For a cascode structure, a normally off silicon device is used in tandem with the gallium nitride device. The VTH of this silicon device dictates the threshold voltage of the overall device. Its pros or advantages include high threshold voltage, and the gate drive is compatible. The gate driver is compatible with that used in silicon IGBTs. However, its advantages include limited speed. Gallium nitride based devices are popular because they can switch at high high frequencies. But because we are using your silicon, again, the silicon limits the speed of the device. And of course, because we are using silicon and gallium nitride together, it will result into higher total cost of fabrication. Another approach is the gate recess misamp. And for this gate recess misamp, its advantages are low leakage, and the VTH can be engineered and tuned. However, these devices are unstable. It suffers from instability, and there is a problem of current and threshold voltage trade-off. One of the most studied device structure for obtaining normal operation is this recess gate AlGaN misamp. Here, the AlGaN layer under the gate is thinned down to deplete the 2-dig channel underneath the gate. The idea, as you can see here in this report, the thinner the AlGaN, the less is the density of the resulting 2-dig along the AlGaN-GaN interface. And thinning AlGaN to below 5 nanometers will eliminate the 2-dig along the AlGaN-GaN interface. Again, the AlGaN layer under the gate is thinned down to deplete the 2-dig under the gate in the channel region, while maintaining the existence of 2-dig in the access regions to maintain the low overall on resistance of the device. To thin down the AlGaN channel, high energy process like dry etching is usually employed. And dry etching of the AlGaN surface is usually carried out using chlorine-based plasmas. Etching proceeds through the chemical reaction of highly reactive chlorine species with AlGaN surface to form volatile gallium trichloride and aluminum trichloride and nitrogen products. Unfortunately, however, extra complicated reactions may lead to the formation of highly volatile NCl3, causing the excessive loss of nitrogen on the AlGaN surface, creating nitrogen vacancies and nitrogen vacancies related defects. Nitrogen vacancies are believed to be one of the origins of donor-like states defects on the AlGaN surface, which when unoccupied with electrons, introduce excessive positive charges at the AlGaN insulator interface. This can regenerate the 2-dig channel in some degree, beating the original purpose of the dry etching, which is to deplete the channel 2-dimensional electron gas. Moreover, electron capture into and emission from these traps due to nitrogen vacancy-related effects can impede the control of the gate over the 2-dig channel, leading not only to lower output current, but also VTH, threshold voltage, instabilities such as hysteresis and transfer curves. The original purpose of recessing the channel is to shift the threshold voltage towards the positive voltage direction to obtain normality of operation. However, due to the excess positive charge due to dry etching, 2-dig is attracted back to the channel, shifting 2-dig back to the negative threshold voltage direction. Also, because etching damage-induced electronic states or traps can cause a scattering of carriers, ID tends to decrease and lose its linear relationship with VGS compared to that what can be expected ideally. So basically, what happens here for these devices, we obtain these transfer curves. Less threshold voltage and lower drain current. Furthermore, using conventional dry etching, it is difficult to control the etching depth. And therefore, the remaining AlGaN thickness in the channel is rather unpredictable. Moreover, there is another problematic threshold voltage drain current trade-off in this conventional recess gate AlGaN-GaN misamps. Decreasing the thickness of AlGaN in the channel can indeed increase VTH, but this also leads to decreased current. This slide shows the actual evolution of the transfer characteristics we observe in our laboratory with decreasing the AlGaN thickness in the channel. The drain current here, the unit is milliampere per millimeter because the drain current is normalized with respect to the device gate width. as the depth, as this depth decreases or increases, the etching depth increases, and the VTH shifts positively. But this is accompanied by drop in the drain current. If we are going to plot this VTH and ID max from these transfer curves, we can obtain this plot, where it is very clear that the increasing the recessed depth increases the threshold voltage in the expense of decreased drain current. This is the well-known VTH ID max trade-off in recessed gate GaN miscent. Meanwhile, Professor Yamamoto and co-workers has developed a technology for obtaining high electron mobility from the grown argon layer grown on etched gallium nitride surface. This is Professor Yamamoto with me inside our clean room. He is actually one of the professors who grew the first high-quality indium nitride, showing the correct band gap of 0.7 electron volts. And I considered him as one of the pioneers of indium nitride epitaxial growth research. We then asked the question, is this regrowth technology developed by Professor Yamamoto applicable to channel region of gate recessed mistemp? This slide compares our proposed device, which we call the recessed regrown channel miscent, or simply RRC. Compared with a conventional device having damage, our proposed device has a fresh interface because of this regrown argon layer, free from the dry etching damage. This slide compares the fabrication process of our proposed device with that of the conventional recessed gate miscent, which highlights that only an extra step of argon regrowth is needed in our proposed device. In conventional device process, the argon thickness in the channel is difficult to control because dry etching is used to form this recessed structure. For the proposed device, the entire argon is removed first, then followed by regrowth of argon. Note that it is easier to control the thickness of the argon channel using regrowth than using dry etching. And again, compared with the conventional device having damage, our proposed device has a fresh argon alumina interface, which we believe has low interface state quality. This slide shows the relevant dimension of the fabricated RRC miscent, while this is the bird's eye view as a SEM image of the device. I have still approximately 10 slides. I think I can finish in 10 minutes. This slide compares the Semilog back and forth ID versus BGS sweep, where we can see that compared with the conventional recessed gate miscents, our proposed device has a smaller hysteresis loop. And this hysteresis in transfer curves is due to existence of electron traps along the insulator argon interface, which suggests the lower density of interface states or traps for our proposed RRC devices. This slide compares the linear scale transfer characteristics of a conventional recessed gate miscent with our proposed device, where we can see that compared with the conventional device, our device has higher threshold voltage and also a higher drain current. The threshold voltage is approximately 5 volts, and the maximum drain current is greater than 400 milliamperes per millimeter. Next, I show you here the output drain curves of the study devices, where we can see that indeed our proposed device has higher ID max than the conventional recessed gate argon GaN HEMTs. For benchmarking purposes, we now compare our results with those results reported in literature. The proposed device showed ID max of about 500 milliamperes per millimeter and a VTH of about positive 5 volts. Here we can see that our device shows a competitive combination of ID Max and VTH, and indeed the only device that showed ID Max up of 500 milliamperes and per millimeter, and threshold voltage of 5 volts, of at least 5 volts. And in conclusion, applying the regrown argon layer developed by Professor Yamamoto and recessed-gate alumina argon GaN systems, we have demonstrated normally of operation with excellent combination of threshold voltage and maximum drain current from our devices. Here I acknowledge the support of JSPS and Toshiba Electronic Devices and the Storage Corporation, as well as the support of my former bosses, Professor Tamotsu Asasumi and Professor Masaaki Kosuhara, and the members, student members of my laboratory. This ends my presentation. Thank you all for listening.
Thank you very much, Dr. Joel, for that insightful talk. And now I would like to remind everyone that you can ask if you have any questions. You can use the chat box to ask questions. So we are moving on to the Q&A. If you have any questions, you can also ask by unmuting. And along with that, I would like to remind you to give us a feedback on this session. By scanning this QR code, you will find the feedback form. Please give your valuable feedback to you. That will help us to organize our future webinars.
Can I ask a question?
Yes, please.
Yeah, thank you. Yeah, thank you very much for a nice talk, Joel. My question is, your title of today's talk includes the word safe, but by safe you mean in terms of a circuit operation, or safety as a material?
Yes, Sensei, because as I've mentioned a while ago, conventional argon GaN amps are normally on devices.
Mhm.
And for normal on devices, there are issues that if problems happens on the gate driver circuits, current
Yeah.
will flow uncontrollably.
Yes.
Cannot control the current
Mhm.
between the drain and the
Mhm.
source.
Mhm.
And in some applications like bridge rectifiers or AC or DC to AC converters,
Mhm.
if the gallium nitride normally on the off devices are used, this can result in the shorting the DC source, and this is pretty much dangerous.
Oh yeah.
So instead of using this normally on devices,
Mm.
we develop the normally off devices using the regrown and the recess structure.
Yeah, thank you. But how is the safety of the material of gallium? Is it safe for human body?
Do you mean in terms of well, compared to gallium arsenide?
Mhm.
Is it for example, gallium arsenide, the source is gallium and arsenic. Arsenic is more poisonous, right?
Mhm.
Compared
Mhm.
to gallium nitride.
Right. I see.
Mm.
Thank you.
We have few questions coming up in the chat. So let me read it out to you, Dr. Joel.
Yes.
So one is the relationship between depth and width different from regrown and conventional processes?
Again, can you repeat that, please?
Is the relationship between depth and the width different for regrown and conventional processes?
The relationship between what? I will again share my slide.
Depth and width.
Depth and
Width, it says
Threshold voltage, VTH.
VTH.
okay.
Okay.
Pressure
Yeah.
voltage.
Okay. Basically, yes. I actually okay. Omitted that that part. Okay, I will show you here.
Shall I stop the okay.
Well, this is for conventional devices, right? As we etch the aluminum gallium nitride, the threshold voltage shifts towards the positive voltage direction. But again, the drain current decreases. For regrown, actually, we have results, but I wasn't able to show it here. Yes, the threshold voltage shifts also positively, but the drain current remains almost the same, which means that there is almost a parallel translation of the transfer curves with increasing depth. That is one advantage of using regrown over the conventional recessed GaN devices. It means that the transconductance for this device, actually the transconductance or GM, which is the slope of ID and VGS, this plot decreases as we increase the depth. But for our regrown devices, the transconductance actually increases.
Yeah. Thank you, Dr. Joel. I hope he got the answer. And so there's another question. I understand aluminium gallium nitride is viable for power and wireless application. And what else?
Again?
He's asking about other applications.
Uh-huh. Can you repeat that, please?
So it says that aluminium gallium nitride is viable for power
Okay.
and wireless applications. So other than that, what other applications are there?
Okay. So again, I will share some slide here. I would like to discuss that actually, but due to time constraints. Share again my slides. Well, actually, GaN here. Gallium nitride is here and aluminum nitride is here. So GaN, aluminum is 25%, is somewhere here. Okay. And for that GaN, the band gap is really huge, 4 electron volts. And what is the implication of having a wider band gap? It's not only you have a higher critical electric field, but it also can operate at higher temperature. Because the band gap, the narrower the band gap, the less is the temperature required to excite electrons from valence band to conduction band. The wider the band gap, the higher the temperature is required to excite electrons from the valence band to the conduction band, which means that the aluminum gallium nitride can be used at high temperature applications. If we try to increase the temperature, actually, what happens is because of electrons are excited from the valence band to the conduction band, the identity of the materials, the N-type and the P-type identity of the materials get lost because of the more carry the excited electrons override the number of the electrons coming from the doping, and the resulting holes also override the original number of holes due to doping. So what results is that the identity of p-type and n-type materials get lost as we increase the temperature of operation. But for AlGaN, aluminum gallium nitride or aluminum nitride, because it has higher band gap, that the identities of n-type and p-type materials remains almost the same, even if we apply, we use this at a high temperature. And also, I believe that gallium nitride is very strong against irradiation, not only high temperature, but also against irradiation. So we can use gallium nitride in space, for example.
So there are other questions coming, so I'll read out a few more. Yeah, there's another question. Could I have your comment on the minority carrier property of the existing gallium nitride film?
I think this question is regarding the switching of gallium nitride. Because the gallium nitride, actually, I discussed a while ago the energy. Sorry. I discussed a while ago that the energy loss can be minimized by just minimizing the resistance. But actually, this is not only the advantage of gallium nitride. Gallium nitride can also be switched very fast because of the very because of the what do you call this? Because of the less minority carriers, which means that the switching losses can also be minimized using gallium nitride devices. And for this, gallium nitride devices are really very much efficient. And also not only that, usually for silicon-based devices like IGBTs, the frequency, the switching frequency is usually around just 20 kilohertz or 20 to 30 kilohertz, switching devices. For gallium nitride, you can use these devices in principle up to greater than 100 kilohertz. And the higher the frequency, actually, the less or the smaller are the capacitances, the transformers, and the inductors or the positives that's required to drive this gallium nitride devices. In fact, also using gallium nitride devices, you can also scale down the chargers compared to silicon-based power supplies and chargers.
And have you observed any effects of interface silicon at the regrown interface? Usually we see silicon pile up at the interface.
Well, this is this is a very interesting question. Why? I think in some laboratories this happens because their MOCVD chamber contains a dopant of silicon. But in our chamber, we don't dope aluminum gallium nitride. There's no silicon. Or also it happens sometimes with when your chamber is using quartz. So silicon enters your algan crystal. But as far as our crystals are concerned, we did not observe any noticeable silicon contamination in our regrown algan layer.
So thank you, Dr. Joel. I think we have about 3 more questions. So one is, How about the IV slope in the subthreshold region compared with the bulk CMOS?
CMOS. Okay, let's see. Okay. Am I sharing my screen now?
Yeah.
Okay. I think this question pertains to the subthreshold swing. Subthreshold swing is also a measure of the interface states of the devices or the traps between the insulator and semiconductor. Okay, this is the subthreshold slope or subthreshold swing of the device. So as you can see here, for the conventional resist gate amps, this is the portion of the subthreshold region. This subthreshold region. Can you see my slide?
No, I think we cannot see it.
Okay, I see. Okay, I will share it again. Sorry. Can you see my
Now we can
slides?
see.
Okay. So again, like the question pertains to the subthreshold swing, which is regarding this portion of the transfer curves. The subthreshold swing is actually a measure of how fast or slow the device can be turned on and off. The subthreshold swings should be smaller. A smaller subthreshold swing means that your subthreshold, the slope here, is almost vertical, right? As you can see from this comparison of our conventional and RCC hemp, this slope of the subthreshold is much vertical compared to this subthreshold slope of the conventional, meaning there is less interface states for our proposed device. But for compared to CMOS, I don't have any idea. We haven't compared the subthreshold slope of our devices to those of silicon CMOS. But one thing is sure here, our devices showed very low subthreshold swing, maybe around just 100 millivolts per decade, and that's pretty much low for GaN-based mishaps.
And is also asking how about the RF performance?
Okay.
Uh,
We did not perform any RF or high frequency experiments on our devices yet, because our target here is power, more on power. But anyhow, that's yes, that's we are planning to do those experiments in the near future.
Mario, I think there's a follow-up question about, is it smaller than 65 millivolts per deck? Just
No,
that's the question.
60 millivolts per decade is the ideal subthreshold slope. So smaller than that, I mean, it's approximately it's actually impossible unless you use some now like well, theoretically it's actually impossible to reach that 60 millivolts per decade, especially for gallium nitride. That's the only comment I can give.
um, there's one more question remaining. Without doping, how the 2DG is formed and what is the source of it at without doping condition?
Okay, I think I explained this a while ago.
Yeah.
Then I will share my
So
slide.
I think, yeah.
I explained this step by step a while ago. Can you see my slide? See my slide?
We can see.
Okay. The two-dimensional electron gas is actually due to the internal polarization fields, which forces the electrons to move from left to right. And actually, when you ask me what is the physical source of this two-deck, this is actually a debate regarding the source of two-deck. In my personal opinion, actually the source of two-deck is due to the surface donors. There's defect level here in Algan. And this surface donor, the surface donor acts as the source of electrons to the two-deck. That's my personal opinion here. I mean, there is a donor here on the Algan surface. And this is a defect. And probably this is due to nitrogen vacancy.
Okay. So I think we have come to the end of the questions, and there are many attendees who are interested in having your presentation slides. So if you are willing to share them, so you can share with us and so that we can share with the attendees. And also Dr. Joel, so there are attendees who are interested in contacting you via LinkedIn. So can you give a comment on that?
And yeah, if you have any questions, you can reach me here in my email. And also, this is the QR code of my laboratory.
So I think many of the attendees will be interested to get in contact with you. So here's your chance to get in touch with Dr. Joel for further questions and any collaborations. Let me share the screen back.
Mm-hmm.
Okay. Now, this is a gentle reminder for you all to give us a feedback through the feedback form given here at this QR code. So your feedback is really valuable for us. So we have come to the end of the session today, and now I would like to invite Professor Akinori Nishihara, a past director of IEEE Region 10, for the closing remarks and the vote of thanks.
Okay, thank you very much, Veronica. And thank you very much, Joel, for a very nice and detailed explanation. Well, I'm not in the field of semiconductor devices, but I felt I understood. Thank you very much. And I'm sure many audience enjoyed your talk. There were more than 120 people here in this webinar. And I'm glad that you are working in our country, in Japan. And yeah, we just before the session, we talked with him in Japanese language. He's very good at Japanese language, and I hope you enjoy living in Japan. And I'm proud of you as a faculty member in the Japanese National University. Okay, so as a token of appreciation, we send this virtual plaque for you, Dr. Joel Asubar. Thank you very much for your very nice talk this evening. Thank you.
Thank you very much, Professor.
And yeah, thank you. And we will announce the next webinar This is the third, and next will be the fourth of Region 10 Talk on Saturday, 20th of May, about a month later. Future directives of offshore wind technology and emerging P2X and energy island concepts. Yeah, please join. Yeah, the link for registration will be sent later, so please join. Okay, that's all from me. Back to you, Veronica.
Thank you very much, Professor Akinori, for the closing remarks and the vote of thanks. So now we have come to the end of our R10 Talk 3. So there are some special people that I would like to thank. So this is the organizing committee and the coordinators of R10 Talk, the team coordinator, Dr. Vimonta, and the team members, Ashwant, Hisham, and Anu. And so from IEEE Region 10, IEEE Region 10 Director, Prof. Lance Wang, and the Region 10 Director-elect, Prof. Takako, and the Vice Chair of Professional Activities, Dr. Zia Ahmed, and also Vice Chair of Technical Activities, Professor Takako Onayo, and IEEE Region 10 Young Professionals Chair, Dr. Zavidya, and IEEE Region 10 Student Activities Committee Chair, Professor Jennifer. And I'm also from the IEEE Region 10 Student Activities Committee. So then again, we have Mr. Rajendra Asthana from IEEE Region 10 Life Members Committee, and Mr. Sanjay Kachaudhary, IEEE Region 10 Industry Relations Committee Chair, and Dr. Janiel from IEEE Region 10 Professional Activities Committee, and Ms. Emmy from IEEE Region 10 Humanitarian Technology Activities Committee, and Dr. Kanita from IEEE Region 10 Women in Engineering Committee. So this is a joint endeavor from all these IEEE Region 10 committees, and this effort has been a success due to all of these members. So I would like to extend my gratitude to all of these committee members for their hard work to make this event success. So with that, I would again would like to remind you to give your feedback on our QR code given here. So, and to connect with us in the future, so you can use all our IEEE Region 10 LinkedIn, Facebook, and YouTube handles, so you can get in touch with us. And so I would like to thank you for your amazing and interactive participation, each and every attendee here. So thank you very much, and join us for the upcoming webinars and workshops as well. So with that, we have come to the end, and I would like to invite all the panelists to have a group photo. Kindly switch on your video so we can have a group photo with the speaker for the panelists. Thank you very much. Dr. Zia, would you be able to open? I'll take one from my end. One more, please. So thank you very much, everyone.
Thank you.
Thank
Thank you.
you.
Plus Lance, thank you.
Bye.
Thank you very much.